Gases are usually introduced in a general chemistry course midway through the first semester. Liquids and solids, on the other hand, are typically introduced much later, usually in the second semester of general chemistry. This is because liquids and solids depend on intermolecular interactions. That's why liquid and solid phases exist, because those particles interact with each other. In gases, however, we can ignore these intermolecular interactions. This makes gases easier to study. Take water, for example. In the liquid and solid phases, water molecules are interacting via hydrogen bonding, which you can see here in the red broken lines. But let's say we increase the energy by increasing the temperature. These hydrogen bonds can be broken. In the absence of hydrogen bonding and higher kinetic energy, the molecules are allowed to move about freely. This is the gas phase. These particles will then collide with the walls of the container they are in. The force per unit area of the collisions of these particles with the walls of the container is the pressure of the gas. For gases, we need to introduce a few properties, the first being pressure. Pressure is the force exerted by an object per unit area. Units of pressure are standard atmospheres, although torr, millimeters of mercury, and pascals are also used. In addition to pressure, temperature is also important. The gas behavior will depend on the temperature in units of Kelvin. Gases also occupy the volume of the container they are in. And of course, the amount of gas is important. Here we'll be using moles to report the amount of gas present. And all these properties are related in various gas laws, which we'll get into next. In 1787, Jacques Charles found a linear relationship between volume and temperature of a gas. Plotting the volume versus temperature data for various gases yielded straight lines. He can only measure down to a certain temperature, however. Interestingly, he noticed that extrapolating the data showed the lines converge to the same temperature at a hypothetical zero volume. This temperature is negative 273.15 Celsius. The result established the Kelvin scale, and this temperature is 0 Kelvin, or absolute zero. In chemistry, temperatures are usually reported in Kelvin, which is the degree Celsius plus 273.15. In 1662, Robert Boyle discovers the first gas law. It is the relationship between pressure and volume. The pressure of the gas is inversely proportional to the volume of the gas. This simply means that a decrease in the volume of the gas, with a piston for example, will result in an increase in the pressure of the gas. And vice versa, an increase in the volume of the gas will result in a decrease in the pressure of the gas. Furthermore, we can multiply both sides by the volume and get the product of PV. This is always some constant. We'll call the constant A here. Recall, gases depend on pressure, temperature, volume, and the number of moles. Let's assume the temperature and the moles are constant. Thus, if there's a change in pressure or volume, this pressure-volume product must remain constant. And this is called Boyle's law. Let's do an example. A sample of helium in a 25.0 liter tank has a pressure of 22.5 atmospheres. The tank is expanded to a new volume of 32.0 liters. What is the new pressure? First, notice how the volume is changing. And the pressure is changing. There is no comment on the temperature nor moles, so we'll assume that those are constant, and we'll use Boyle's law. We are looking for the new pressure, or P2. I can divide both sides by V2, and this will leave me with an equation for P2. I can now insert my initial values in the numerator and final volume in the denominator. This gives me a final pressure of 17.6 atmospheres, which makes sense. The volume was increased, thus the pressure decreased. In 1787, Jacques Charles observes the relationship between volume and temperature of a gas. The volume of a gas is directly proportional to the temperature of the gas. This simply means that an increase in the temperature of the gas will result in an increase in the volume of the gas. And vice versa. A decrease in the temperature of the gas will result in a decrease in the volume of that gas. Furthermore, we can divide both sides by the temperature and get the ratio of volume over temperature. This will always yield some constant. We'll call that constant B here. Recall, gases depend on pressure, temperature, volume, and the number of moles present. Let's assume the pressure and the moles are constant. This ratio must always be constant. Thus, if there's a change in the volume or temperature, the product must remain constant. This is called Charles's law. Also of note, the law is true for temperature in Kelvin. In this example, a 3.0 liter sealed balloon at 23.0 degrees Celsius is cooled to 5.0 degrees Celsius. What is the new volume of the balloon? The first thing I'll notice is that I'll have to convert the temperatures. I'll first convert the temperatures to Kelvin by adding 273.15 to each Celsius temperature. The initial volume is given in the problem, and I'm looking for the final volume. Pressure and moles are not mentioned, so I'll assume that they are constant, and I'll use Charles's law. I'll multiply both sides by T2, and this will cancel the T2 on the right side, leaving V2 by itself. I can insert my values into the equation and see that the final volume is 2.8 liters. This makes sense. As the gas is cooled, the volume decreases. The volume is directly proportional to the temperature. In 1811, Avogadro observed the relationship between volume and moles of a gas. The volume of a gas is directly proportional to the amount of gas in terms of moles. This simply means that an increase in the moles of a gas will result in an increase in the volume of that gas. And vice versa. A decrease in the moles of a gas will result in a decrease in the volume of that gas. Furthermore, we can divide both sides by moles and get the ratio of volume over moles. This ratio always equals some constant. We'll call that constant D here. Recall, gases depend on pressure, temperature, volume, and moles of a gas. Let's assume the pressure and the temperature are constant. This ratio must always equal a constant. Thus, if there's a change in the volume or moles, the product must remain constant. This is called Avogadro's law. Let's do an example. A 24.0 liter tire contains 0.90 moles of nitrogen. Nitrogen is added, and the final amount is 1.15 moles. What is the new volume of the tire? The initial and final moles of nitrogen are given in the problem. The initial volume is given in the problem, and I'm looking for the final volume. Pressure and temperature are not mentioned, so I'll assume that they are constant, and I'll use Avogadro's law. I'll multiply both sides by N2, and N2 will cancel on the right side. This leaves V2 by itself. I can insert the initial volume times the final moles divided by the initial moles. This gives me a final volume of 31 liters. This makes sense. More moles of gas are added, thus the volume increases. Volume is directly proportional to the moles of the gas.